So the last topic, very important of chapter 5, is how to find a distribution of a function of a continuous random variable. Okay, so sounds a little bit vague at this point, but once we see those results and examples, I think you will see what we mean by this. And pretty much you start off with, like, say, capital X as a continuous random variable, and you know it's PDF. Okay, so you know fx. Okay, but now all of a sudden a gx, a function of x, comes along, and then you're asked to derive the distribution of the gx function. Okay, so very important theorem. Okay, on finding the PDF of a function of gx, I'm going to go over the theorem first, talk about any exceptions, and then go over two examples. Okay, so suppose x is a continuous random variable with PDF fx. Okay, so here notice we're using subscript just to highlight that this f is about x. Okay, so if a function, so notice the theorem has two conditions here, is monotonic. Okay, so increasing or decreasing, but not both in on the range. Okay, and also differentiable. Okay, so that means it is a continuous function. Then the random variable, okay, defined by, so if I use y to represent gx, okay, so the y random variable gonna have a PDF of this. Okay, so notice the different notation here. Okay, and I highly recommend you start to add those subscript of the random variable now to the PDF and CDF, because, well, now we're working with two, so you better make sure that you work with the right one. So here what we're saying is that the PDF, okay, of y, so we have f capital Y as a subscript. Okay, so PDF of y equals to the PDF of x multiplies with the absolute value of dx over dy. Okay, so look at this result. I guess you will start to think, okay, obviously I need to know the f. So in order to know fy, right, I need to know fx, right, and I also need to, well, do the derivative, right, of dx over dy, and then take the absolute value of it. Okay, so this is, keep in mind, you need to satisfy these two conditions in order to use this result. Okay, and we'll see two examples. One you can use it, the other one you cannot. So when the case comes up that you cannot use the result because either the function is not monotonic or is not differentiable or both, then another way you can do it, just to go back to why this is the case here, is that if we are trying to find the fy, okay, given fx, okay, so pretty much what we're doing, okay, is just related to this part, okay, is, well, we're trying to get the fx, right, evaluated at the inverse function of y, okay, because x, well, y is gx, right? The inverse function, we know that x is g inverse y. Okay, so pretty much this is what we're doing up here. Okay, so so fx, okay, you evaluate at y, which is the inverse, evaluate at x, which is the inverse of y, and then when you're doing the dx over dy, you're doing over here. Okay, so this is why it works. Okay, but I will show you soon with like the second example once we get to it, to show that, well, if you cannot use the result, you can use a go back to the definition of fy, the CDF of it, and then take the derivative in order to do the result, okay, the derivation. Okay, so the first example, like I said, you will be able to use the theorem. Okay, but let's look at y. Let x to be a uniform between 0 and 1. Okay, they're asking you about the distribution of y is negative ln x. Okay, so just log x. Okay, so in order to use the theorem, okay, we need to check the conditions. Okay, so remember here gx is negative ln x. Okay, and on the left, I'm just showing you the gx function between 0 and 1, because we know that x is uniform between 0 and 1. Okay, so if you look at this function, it is indeed monotonic decreasing, right, and differentiable all over the entire range. Okay, so what that means is that you will now be able to use the theorem, and let me just write the theorem up here so we know what we're working towards too. Okay, so you want to get fy from fx, right, and then dx over dy. Okay, all right. So this is the theorem. Okay, and now we're ready to use it. So let's look at how each piece can be found. Okay, so first of all, we know that gx is negative ln x. Okay, so I would say, because eventually you will need to do dx over dy, right? So you wanted to express your x in terms of y. Okay, so that's why you want to, first of all, I guess, find the inverse function of y. Okay, so gx equals to negative ln x. Okay, so if I want to try to find the inverse function, meaning that I want to express my x in terms of y, then we're gonna do y equals to negative ln x, right? And then I take, I guess I take the exponentiate both sides, right? And then take the like the negative sign correctly, and then I will get the inverse function of x equals to g negative y. Okay, so what that does, like I said, is trying to get the inverse function. So later on, we can actually take dx over dy. Okay, now we are ready to do it. Okay, because now you already express x in terms of y. Okay, so because of that, we take the order, first order derivative, right? dx over dy is going to be, so take the derivative, right? E to the negative y with respect to y. So we get negative e to the negative y. Okay, but don't forget the formula asks you to do the absolute value of it. Okay, so eventually later on when you actually use it, it's going to be e to the negative y. Very easy. Okay, all right. So that's good. And that's pretty much all of it already, right? Because we have done this part, right? And then this part is a uniform anyway. So that whole thing is just one, regardless of where your x or y is. So in order to complete the entire task, you will see that this is the PDF, okay, of y, okay, because fx times this, and fx is 1 because it's uniform, okay, and then it's negative, and like it's negative e to the negative y, and then we take the absolute value of it, so it just becomes e to the negative y, okay, and don't forget, okay, we always need to show what the range of the new random variable is, okay, so for us is 0 to positive infinity, including 0, okay, and so when you're trying to write the like express the entire part of the PDF, you should not only just show the PDF itself, but also the range, okay? Alrighty, so let's look at another example. Like I said, the other example will be the case that you cannot use it. And if that happens, what you're gonna do, all right. So let x have PDF of fx, okay? And on the real line, okay? We want to find the PDF of x, y equals to absolute value of x. Okay, can we use this formula? Okay, I already told you, well, no, but let's see why. And then if this happens, what we can do. Okay, so remember the two conditions, right? You need to check if it's a monotonic and whether it's differentiable. In this case, it's actually not monotonic because if you graph it, okay, because it's absolute value of it, well, it's not monotonic because the first half is decreasing, the second half is increasing, right? But also it's not differentiable at 0, okay, at this point. So we won't be able to use the formula, okay, unfortunately. But like I said, when this happens, you should always go back to the definition of fy in the first place, if you remember, is that it's the first order derivative of the fy divided by y. Okay, so if in order to find the PDF, right, my first, like, I guess, last resort is always going back to the CDF itself to make sure that we can express it and then take the first order derivative. Okay, so for this case, let's see what we can do. Let me erase this. Okay, so we're going to find the CDF of y and then take the first order derivative to get the PDF of y. Okay, so for any y greater or equal to 0, okay, in our case over here, okay, fy, okay, so again, this is capital F, so this is CDF, okay, so this y over here, right, if I want to know the CDF up to this point, right, it's going to be equivalent of trying to find the probability of x is between negative y and positive y, okay, and this is, as you know, because we're looking at the PDF over here, okay, sorry, the CDF, okay, so CDF, let me just write it out, maybe one more step before going over this. Right, we know it's integral, right, from infinity to, okay, now it's probably a good chance to good time to use different notation. So let me use y over here, but then I will use ft t dt. Okay, all right, so the reason why this is the case is because y is absolute value of x. Okay, so that is the same as, so if I'm trying to find this probability, right, the CDF of y, it is equivalent over here to show that I'm trying to figure out the probability of X is between negative Y to positive Y, just because, well, you will see that we want, so we want, let me do this. This is probably easier to do by, instead of doing the CDF, oh, let me erase this just to make it clear, okay? So the CDF, okay, is the same as trying to get the probability, right? I'm getting the probability of my Y is smaller than Y. Okay, so this is all good, right? This is the random variable about capital Y, okay? I'm evaluating at Y, okay? And this is equivalent to what I'm showing on here, because Y equals to X, absolute value of X, okay? So, well, because Y has to be smaller than Y, right? Capital Y has to be smaller than Y, so that means X needs to be smaller than Y, absolute value of X, right? So that is the same as doing this, okay? So that's why this is true, okay? And notice that one very important thing that we have done is not only we express the random, like not only that we're able to do the algebra and show this, but also because now if we come to this point, the random variable becomes X, right? When the random variable becomes X, we can use everything about the PDF of X or the CDF of X, okay? So here we're using the CDF of X mostly because, well, you can see that because I'm trying to find the probability of X between negative Y and positive Y, right? And I know the PDF of a small fx, then the CDF is capital FX, right? So to get the probability is the same as evaluating the CDF at the larger value minus the smaller value. Okay, so this is a key point, okay? You need to use the fact that Y equals to X, absolute value of X, okay? And then from there, you're able to recognize how you're getting the F, capital Fy for in terms of capital Fx, okay? So now we have found the CDF, okay, in terms of X. Okay, that's great. So the next step is to find the PDF, right? So we take the first order derivative. So to do that, okay, we are simply just taking fxy minus fx negative y, right? The whole thing, take the first order derivative with respect to y. Okay, so with respect to y, remember this is a CDF, right? So if I take the first order derivative, it becomes the PDF. Great, okay, and the second here, again, it's a CDF, but it's negative Y, and then we're taking the first order derivative as well with respect to Y. So this, just because of the function, we have a negative over here, so this becomes fxy plus fx negative y, okay? And then you're done, okay? So in this case, like I said, it's pretty, like, first of all, you need to realize that, well, we cannot use the formula, so forget about it. And then if that happens, the golden rule, like I said, is always to find the CDF and then take the first order derivative to get the PDF. Okay, to find the CDF, it requires you to think hard, right, about the relationship between X and Y. Okay, so the CDF of Y, you can always express it by doing like what I did earlier, right, is Y smaller than Y. Okay, and then Y, this is a constant Y over here, and then capital Y is the random variable, and then you know the relationship between them too, so you're able to go from here to express, right, the CDF of Y in terms of CDF of X. Okay, and then CDF of X is known because you're given, okay, and then the next step is taking the first order derivative. All right, so on the live exercise session, you will see other examples, so make sure that you explore all of them, and good luck with everything.